You ever feel like there's some kind of hidden rule book for the universe? You know, a set of instructions that decides how a ball flies, how a car turns, and, well, why you don't just float off into space. Turns out there is. And today, we're going to pull back the curtain on these invisible laws that are secretly running everything around us. So let's just dive right in with a question for you. What could firing a bullet possibly have in common with you just walking across the room? I mean, on the surface, they seem like total opposites, right? One is explosive, incredibly fast. The other is, well, it's just walking. But what if I told you they're basically the same thing? Here's the secret. They both follow the exact same simple and totally unbreakable rules of action and reaction. And that's what we're going to dig into today. These powerful ideas from Sir Isaac Newton that are basically running in the background of your life every single second of every single day. All right, before we jump into the laws themselves, we got to get on the same page with a few key ideas. Think of these as the building blocks: motion, pushes, and pulls. First up, the real basics: rest versus motion. It's pretty intuitive, right? A stone on the ground, it's at rest, because compared to you and the ground, it's not going anywhere. But a train pulling out of a station, that's definitely in motion, because its position is changing. It seems simple, and it is. But this distinction is basically the starting line for all of physics. Okay, let's get a little more specific. Imagine you're wandering around a park. The total path you take, all the twists and turns, that's what we call distance. It's just a number, like I walked 2 miles. But displacement is different. That's the shortest straight line path from where you started to where you ended up. See, it has a distance and a direction. That makes it a vector. And this is super important. In physics, the direction you're going matters just as much as how far you go. And that brings us to the main character of our story today, force. It's really simple. It's just a push or a pull. That's it. It's the thing that makes objects start moving or stop moving or change direction. And just like we saw with displacement, force is a vector. It has a direction. You don't just push on something, you push on it in a specific direction. So it turns out all these pushes and pulls come in 2 main flavors. You've got your contact forces, which are exactly what they sound like. Things have to actually touch. And then you've got the more mysterious non-contact forces. Think about gravity or magnetism. They work from a distance, across empty space. Let's run through a few examples, and I promise you'll start seeing these everywhere. First up, friction. That's the force that fights you when you try to slide a book across a table. At the exact same time, there's another force at play. The normal force. That's just the floor pushing back up on you, keeping you from falling through to the center of the earth. You're literally feeling it right now. All right, next up is tension. The easiest way to think about this is a game of tug of war. That force pulling through the rope? Yep, that's tension. It's in any cable or string or chain that's being pulled on. And what about springs? They're kind of cool because they can do both. They can push and pull. If you squeeze a spring, it pushes back. If you stretch it out, it pulls back. It's always trying to get back to its original, its comfortable shape. And of course, we've got the most dramatic contact forces of all, collisions. When 2 things smash into each other, for that tiny, tiny fraction of a second, they exert these huge forces on one another. Okay, so with those building blocks in place, we're ready for the first big rule. This is Newton's first law. I kind of like to call it the law of laziness, and you'll see why in a second. The whole thing revolves around one key idea: inertia. Okay, let me ask you this. You've definitely felt this. You're riding in a car, everything's fine, and then the driver slams on the brakes. You lurch forward, right? Feels like you got thrown. So, what's really going on there? The answer, in one word, is inertia. It's this built-in property of everything that basically makes it stubborn, or lazy if you prefer. An object that's not moving wants to stay not moving. An object that is moving wants to keep moving in a straight line at the same speed. Things just want to keep doing whatever they're already doing. They resist change. That's the heart of Newton's first law. So let's go back to that car. Here's what's happening. Your entire body is cruising along at, say, 60 miles an hour. When the driver hits the brakes, the car stops. The seatbelt and the seat stop your lower body. But your upper body, because of inertia, it just wants to keep going at 60 miles an hour. So you're not actually being thrown forward. Your body is just trying to continue the motion it already had a second ago. And this isn't just about moving objects. It works for things that are sitting still, too.
You've probably seen this classic trick, right? You put a playing card over a glass, a coin on top of the card. If you flick that card out of the way fast enough, the coin's inertia, its stubbornness to stay put, takes over. The card shoots away, and the coin drops straight down into the glass. That's inertia of rest.
All right, now let's jump ahead to Newton's third law, which is all about how forces are never lonely. The big idea here, and I mean this literally, is that forces always come in pairs. It's a two-way street. A force can't exist by itself. And this leads to one of the most famous sentences in all of science, and for a very good reason. Newton said, "To every action, there's always an equal and opposite reaction." It's this beautiful, profound idea. It means every single push is met with an equal and opposite push back. Here's a brilliant way to see it in action. If you take two of those spring scales, for weighing things, and hook them together and pull, they will always show the exact same reading. Always. The pull from scale A on scale B is perfectly matched by the pull from B back on A. It's not just a good idea, it's a fundamental rule of the universe. Okay, but this brings up a really common question. If the forces are equal and opposite, why doesn't everything just cancel out? Why does anything move at all? And here's the absolute key. The action and reaction forces are acting on different things. Think about it. When you walk, your foot pushes backward on the earth. That's the action. The earth then pushes forward on your foot. That's the reaction. That force is enough to move you, but you're not nearly massive enough to notice any change in the earth's movement. They don't cancel because they're not acting on the same object. And this is where it gets so cool, because this one law explains both the most ordinary and the most incredible things. It explains how you walk. You push on the earth pushes on you. And it's the exact same law that explains how a massive rocket launches into space. The rocket pushes super hot gas down, and the gas pushes the rocket up. It's this same principle, just taken to a whole new level. So, let's wrap this up. What's the big takeaway here? What should you remember from all this? Is this. These laws aren't just for a physics class or some dusty textbook. They are the invisible operating system running the entire physical world. It's happening in the background of every single thing you do. Every step you take, every time you throw a ball, every single moment. This stuff is at work.
So from now on, I want you to look at the world a little differently. It's just full of these little physics puzzles. The next time you see something move or stop or change direction, just ask yourself, okay, what's the rule that's making that happen? Now that you can see the rules, what else out there can you explain?